This is example 6. A single-acting, single-cylinder positive displacement pump is used to drain an excavation. The pump has a bore of 150 mm and a stroke of 400 mm. The suction and discharge pipe are both of 50 mm diameter, the suction pipe being 2 meter long and the discharge is 6 meter above the level of the water excavation. The suction lift to the pump is 1.5 meter. In the absence of any chambers or either A, pump suction or B, discharge, calculate for A and B the absolute pressure head in the cylinder at the start and at the middle of each stroke if the pump drive is at 0.2 revolution per second and may be assumed to be simple harmonic. Also determine the maximum pump speed if separation is to be avoided on the piston face. Assume a friction factor of 0.01 for both pipe and atmospheric pressure of 10.3 meter of water and a fluid vapor pressure of 2.4 meter. So we have a question of this one. And then we need to calculate the pressure head here, okay, in the cylinder at the start and middle for each stroke. So each stroke mean at the suction stroke and also at the delivery stroke. So because previously in previous question, so we only calculate the absolute pressure head for the suction stroke. So this is the diagram for the question. So we have a suction head as 1.5 and then for the delivery head here we need to deduct with 1.5, so we have a 4.5 for the delivery head. So a general expression for the absolute head in the cylinder during the suction stroke may be written as below. So here this is the general equation for the absolute head in the cylinder. So we have atmospheric pressure minus with the suction head minus with the acceleration head, and then because we already know to calculate the friction, so we need to minus the friction head for in the suction. Okay, in previous question, because I'm not show you yet the calculation of the friction, so we just calculate until the acceleration head. But now you already know how to calculate the friction at the suction and delivery, so you need to include the head of this all of these, the suction head, the acceleration head and also the friction head to calculate the absolute head in the cylinder during suction stroke. So and then what is the meaning of the simple harmonic? So means that it can be represented by sinus wave line or sinusoidal pattern. Okay. So we could go a little bit faster here. So cylinder head at start of suction stroke. So we know that the velocity is 0. So and then we know that the atmospheric pressure is 10.3 and then the suction head is 1.5. So the acceleration suction head can be calculated like this one. So because the value of cos is actually equal to 1. Okay, so we have cos 1, the 0 angle here, so the value of cos is equal to 1, so we could calculate the acceleration head is equal to 0.579 meter. So and then we could calculate the friction suction at the beginning here. So here, because we have a very specific point at the beginning, at the center and at the end of the stroke, so means we know the location, we know the value of theta. That's why we need to calculate the friction here by using this equation. So you could see in previous question, we don't know. We have no specific point to calculate the friction. That's why we could calculate the average friction for that problem. So here we have a sine omega t. So we found that sine omega t is equal to 0 here. So we could say that the friction is equal to 0. So it is very simple. You know that at the beginning, there are still no movement of the water. That's why the friction is equal to 0. So and then we could find that at the beginning, so the pressure head here at the cylinder is equal to 8.221 meter of water. So please bear in mind, so this is actually in absolute pressure. So actually this is actually below the atmospheric pressure. So and then we could calculate the cylinder head at end of the suction stroke. So you could check all these parameters. So we still have acceleration head in negative. So and then the friction is also equal to 0. So and then we could get the value is 9.379 meter. So and then this is the cylinder head at mid suction. So we substitute everything here. So we could get that the friction for the mid stroke is actually equal to this one. So and then we could calculate that the friction head and the pressure head for the suction in the middle stroke is equal to 8.696. So if you see all this value, you will find that at the beginning here, okay, at the beginning here, it is 8.2 meter. So at the end, it's 9.379. So this is 8.2. And then at the middle, it will become 8.6. So you will find that the value is actually increased. So you must understand that the pressure is actually in absolute pressure. So mean that the increment of the value is actually show that the suction is actually become weaker and weaker. Okay, so because it's going to be or to become same value or same amount of the atmospheric pressure. And then, so this is new for us. This is new for you. We need to calculate the absolute head in the cylinder during the discharge motion. Okay, previously we calculate during the suction, but now we need to calculate during the discharge. So in discharge, you must remember or you must know that to push water above its own level is actually a very hard work. You need an extra energy to push water to the upper level. That's why to calculate the absolute head in discharge part, we need to add all these parameters. So we need to overcome the atmospheric pressure. We need to overcome the discharge. We need to overcome the acceleration at discharge, and we need to overcome the friction. So means that we need to develop a pressure which could overcome all of these parameters. So that's why for the absolute head inside the cylinder, for the discharge or for the outlet pipe, we need to add the atmospheric pressure with the discharge head, acceleration head, and also the friction at the delivery pipe. Okay, we could start to calculate that one. So we have the atmospheric pressure as 10.3. So we could have the delivery head is 4.5. So you could refer to the diagram. And then we could calculate the acceleration head by using this equation. So we have at start, so the theta is equal to 0. Okay, you just imagine it is the piston is actually moved from the right to the left. So the angle is we assume that it starts with a 0 degree. So and then we could calculate as this one. So we get the acceleration head for delivery is 4.347. So we need to calculate the friction. Okay, we substitute all the value. We get it is equal to 0. Then the pressure, absolute pressure inside the piston is 19.147 meter. And then we could calculate the absolute pressure at the end of the discharge stroke. So we have it is 10.453 meter. Okay, and then you could see that at the end of the discharge, so the pressure is actually almost the same with the atmospheric pressure because there are no more left inside the piston, and then it is equal to the atmospheric pressure. So that is the idea. So and then for mid-discharge stroke means at the middle of the motion, in the middle of the discharge cycle, we could calculate the friction as this one. Okay, so and then we could get it is 0.721 meter. So the pressure is actually 15, means intermediate between the starting and the end of the discharge cycle. So and then we need to calculate this one. What is the safety pressure? So we know that it is equal of this one. So we have H is equal to atmospheric minus suction minus acceleration and minus friction as the acceleration. So we get that the omega here, okay, we just replace this equation for the friction by using this equation, and then we found we have the omega square. So and then we could calculate the omega square here is equal to 17.44. So and then we could get it is equal to 4.176 radian per second. So and then it is equal to almost 39.87 revolution per minute. So we could write as 40 RPM. So this 40 RPM is the maximum pump speed that can be operated without any separation occur inside the piston. If the speed is more than 40 RPM, so means separation will occur inside the piston. Today I would like to share with you example 7. A single-acting, single-cylinder positive displacement pump driven at 0.4 revolution per second has a bore of 200 mm and a stroke of 500 mm. The suction and discharge pipe are both 100 mm in diameter. The suction leaf is 0.4 meter and the suction pipe is 3 meter long. The water is discharged at a point 20 meter above the pump level by means of a pipe 200 meter long fitted with a large air chamber 20 meters from the pump. Calculate the absolute pump cylinder pressure at the start, end and mid-stroke, time for both suction and discharge assuming no slip at the pump, and a friction factor of 0.008 for both pipes. Take atmospheric pressure as 10.3 meter. So in this question, we have this problem. You need to calculate the pump cylinder pressure at the start, end and mid-stroke for suction and discharge cycle. And then we have a friction factor here. We already learned about the friction factor, means the major loss in pipe in fluid mechanics 1. So and then in this problem we have a large air chamber. So air chamber here is actually the air vessel. So the diagram of this problem is shown here. So we have 0.4 as the suction head, and 20 meter here is the delivery head, and then we have a piston pump, and then the most important things that you need to understand here, we have an air chamber here, but it is located 20 meters from the piston. In previous question, the air vessel is located near to the piston pump, so means it's located around here. But in these problems, the location of the air chamber is 20 meter after the piston. So and then we could calculate the pressure here as this one. So we have first we analyze the suction stroke. So the head here, the pressure head can be calculated by this equation. So because I already explained previously, in suction we need to create a vacuum. So means that we need to have pressure less than atmospheric pressure. So the equation will become like this. So mean we have the atmospheric pressure. We deduct with the suction head. We deduct with the acceleration head. And then we deduct with the friction head. So, and then we have three conditions at the beginning, at the middle stroke, and at the end. So means we need to understand about the degree, the angle of the crankshaft, because it will give us different value of sine and cos. Okay, so until this level, I think you already know at start point, the theta is equal to 0. And then we will have a sine 0. So we have a friction 0 here. And then the acceleration. So we could use the idea of this one, because the acceleration will use the equation of cos theta. So at 0, the cos theta is equal to 1. So the equation will become like this. We substitute the value and then we get the acceleration head as 7.968. I'm sorry, the acceleration head is 1.932 meter, and then the absolute pressure head at the beginning is equal to 7.968 meter. So and then I simplified the calculation here. You could calculate for the end of the suction. It is 11.832 meter. So and then at the mid stroke, okay, so this is the value of the friction head, because the acceleration head is equal to 0. So and then we could calculate at the middle is 9.823 meter. So here again you could see that at the beginning, so it is 7.968 meter. So here please be careful, because you will find that the value at the end is higher compared to the value at the start. So because it is the absolute pressure. So mean the lower the value of the pressure head means the higher the suction strength. Because the value, the amount that near or near the value of 0, it is more will have more suction power. So this is the calculation for the pressure head at the piston in suction stroke. So and then we go for the discharge stroke. So again, I hope you could understand this one. I already explained it before. In discharge stroke or in delivery stroke, so we need to push the water to the upper level. So means that we need to create more pressure to make sure that it can push water to the higher level. So means that the calculation of absolute pressure inside the chamber need to overcome all these items. So first, we need to overcome the atmospheric pressure, and then we need to overcome the delivery head. So at least the energy, the power we need to supply to the water, at least need to overcome the atmospheric pressure, the delivery head, the acceleration head, and the friction at delivery. And I add here another item, which is the steady friction. Why we need to overcome the steady friction? Because it is due to the existence of the air chamber. because of the existence of the air chamber. So I already explained the air chamber here will make the flow steady. So means that from this point, the flow is steady. Okay, so before the air chamber, so the flow here will based on the positive displacement calculation. That's why in this calculation, I give you two types of friction. One is friction because the flow is still following the sinusoidal sinusoidal pattern, because there are no air vessel on that pipe. And then after the air vessel, the flow will become steady, and then the friction will become lower. So, and then we need to calculate the friction here due to the common calculation of friction in pipe, as we learned in Fluid Mechanics 1. So that's why in this calculation, I expand the idea of friction head here into two types of friction. One is friction due to the positive displacement pump, and another one is due to the steady flow in pipe. Okay, so if there are no air chamber, there are no air vessel, the steady friction here is equal to 0. So we could calculate the start stroke here. So, and then because the U is equal to 0 at start of cycle, friction loss appear to be 0. However, the action of the air chamber is to maintain a steady discharge from the system. Thus, discharge can be calculated as below. So first, we need to determine what is the flow rate inside that pipe. So we could calculate the flow rate by using this equation. So, and then we could get that it is equal to, okay, so this is the calculation. Okay, so because we have a little bit problem, because from the question, we do not have the RPM, revolution per minute. What we have is actually RPS, according to the revolution per second. Okay, so and then you could substitute the value of RPS, which is equal to this one, omega over 2 pi. So and then the equation for Q can be simplified as this one. Okay, so this is the equation, the relationship between the U, the linear velocity with the rotational speed. So U equal to R omega equal to pi dn over 60. So for this equation, we need to divide by 60 here because the n is in RPM. So as this one revolution per minute. But if the equation is given, if the data is given in revolution per second, so your equation will become like this. Okay, please do not divide it by 60. Okay, so this is an extra equation for your understanding. So, and then this is the equation for major loss. So we learned about this in Fluid Mechanics 1. So I hope you still remember the losses in pipe is F L over D V square over 2G. So and then we could calculate the velocity here, the velocity inside the pipe. So you must understand, if you want to use this equation, please make sure that the flow is steady, means the flow after the air vessel in the outlet pipe. So and then we know that the Q, we already learned that Q1 is equal Q2, so means that A1 V1 is equal to A2 V2, and then we could write an equation like this one. So means that cross-sectional area of pipe times velocity of pipe will be equal to the flow rate calculated like this one, means calculated inside the piston. So we have cross-sectional area from piston times r omega over pi, mean the velocity of the piston. So and then we could get this equation. you could fulfill this one, and then okay, so and then we substitute the equation into the major loss equation, which is this equation actually. Okay, so and then we could simplify the equation like this one. So and then again, because this equation is actually for the steady flow, so means that the according to the flow after the air vessel, so means that the value of L here need to be deducted. So means we have a piston here, and then we have an outlet pipe like this one, and then we have an air vessel here. So the distance is 20 meter here. The total distance is 200 meter. So means that for L here, we only need to take the distance from the air vessel to the outlet. So mean it is equal to 180 meters. So and then we could calculate the equation according to this one. So we know that the atmospheric is 10.3. So we have the delivery charge is 20, and then the acceleration head will can be calculated as 12.88 meter. So and then the friction, the delivery friction is equal to 0 because the movement is not start yet. So and then because we have air chamber here, so and then the friction is in steady flow, and then we need to calculate the friction of the steady flow like this one. So and then again you need to understand that when the steady flow, so means that it is mean that water is flowing with same amount all the time. So mean it doesn't matter whether your piston in starting point or at the middle point or at the end point, the friction is constant, is steady. So mean the value of friction is almost the same for all the time. So that's why we need to calculate the steady friction flow here, okay, by using this equation, and then we get it is equal to 0.47 meters. So and then we could get that the pressure at the starting point to push the water up to the upper level, it is equal to 43.65 meters. So and then we could calculate the pressure head at the end of the discharge stroke. Okay, you could have you could try to calculate this one. You will get 17.89 meter. So and then the pressure head at the mid discharge stroke, mean at the middle. At the middle point, you will get the friction delivery friction here is equal to 0.52 meter, and then you could calculate this one as 31.29 meter. So again, I hope you could see the numbers here. So mean at the start, okay, the pressure is high, and then at the middle, okay, we have at the middle here, it is a little bit lower, and then at the end, so it will become the lowest value for the discharge cycle.